Hello everyone and welcome to our next session of our Digital V-Days. I'm very happy that you took the time to participate in our today's session about measuring and displaying the surprising impact of DC bias on the performance of SMT EMI suppression ferrites. I'm also very happy to welcome Lee Hill, who is working at Silent Solutions or who is also the CEO of Silent Solutions. So yeah, very happy to welcome you, Lee. Hi.
Hi, Marcus. How are you?
Yeah, I'm doing good. How are you? You ready?
We are ready to go. I'm here in our video studio in Amherst, New Hampshire. It is 8:30 in the morning. I had to get here early to set up, and I'm ready to go.
Perfect. That sounds perfect for me. So just before we start into the presentation, just some information from my side. You will be muted during this webinar. So this means that you cannot ask us your questions via the microphone, but just put them in the chat and we will answer them later on in the live Q&A. So the presentation will be about 30 minutes long, and then you have the opportunity to get the answers to all your questions. And if there are any questions left, then just email us. And yeah, we will also show you the email at the end. And yeah, then I think we are ready to go. I wish you an exciting webinar. Lee, the stage is yours.
Thank you very much, Marcus. Good to see you again. And welcome, everybody. Thanks for joining Würth Digital Days here online live. During COVID, we had to build this video studio because our online training couldn't be done in person. And so we built this facility so that we could do online training with all of our customers here in the US and around the world. And it's great to do it live through Würth online to meet with all of our friends in Europe and other time zones where you're joining. So we're going to get started here, and I've got some fun demonstrations here during the presentation. Whenever I give a training in EMI, I always like to include hardware demonstrations to show how things work. The surveys that we conduct with people who attend our courses say they always love the demonstrations. So what's going to come up during the presentation is I'm going to use a very small network analyzer here. It's connected via USB to my laptop that I'm using to present. We're going to go and take a look at the performance of an EMI suppression ferrite in a little homemade test fixture here that I built many, many years ago. And along with the test fixture, we have a DC bias power supply that I can command from the computer, and you'll be able to see the amount of current flowing through the EMI suppression ferrite. And because we developed the studio for online training, we wanted to make sure that you could have the best possible view of what's going on. In an in-person course, I don't let you jump up on top of my demonstration table to see what's going on. So in an online class, it's actually even better because you get to see exactly what's going on. You can even read reference designators when we use different demonstration circuit boards. So that's what you're going to see during this presentation. We're going to take a look at impedance versus frequency under DC bias live. No recording, no videos. We're going to do it right here live together. Okay, so back to the presentation here. I only have a half an hour, and at the end of the half an hour, we'll take a look at the questions that you've chatted in. And if there's too many questions, that's always a good thing. As Marcus said, we'll take them, and answer them afterwards, I think by email. So thanks again for joining. Just a tiny bit about Silent Solutions. I started the business in 1992 in Silicon Valley, and I'm talking to you right now from Amherst, New Hampshire. Where the heck is that? It's about an hour northwest of Boston. So when I fly to visit Marcus at Würth and Waldenberg, I fly out of Boston. And in 2017, we started Silent Solutions GmbH, and that's where I'm going to be later this year. And we'll be holding an open enrollment class with Würth in Freiham. So you can come to that if you're interested in more EMC training. At Silent Solutions, we do two things. We help people design things, we fix noise problems, and we do teaching. So if we're going to use EMI suppression ferrites in design, we should know how they work. If we're going to use them for troubleshooting, we should know how they work and what might happen if we use them to filter DC power. We can use EMI suppression ferrites to help us pass regulatory noise tests. We can use them to help us fix noise problems where a system interferes with itself. And we work on these sorts of noise problems. Okay, and we teach a lot of classes. As I mentioned, I'll be in Munich this fall. I also teach the University of Oxford through our university here in Worcester, Massachusetts. And blah, 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 a lot of different places. So I do a lot of teaching in EMC. That's my background. I've been doing this for over 30 years, doing hardware design, troubleshooting, and teaching. And we love working with Würth Elektronik because they are so good in the design space. They have such great technology and people. You'll see this in the handout. Here's a listing of all the courses coming up. Okay, that's the end of what we call shameless marketing. I have a poll question, something for you to participate. I always want classes to be live. I want them to be fun. I don't want to have blah, 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 and people not interested in the audience. That is not how our courses work. So to get you involved, there's one live poll question, and Marcus is going to help me run that from within our presentation platform here. Don't worry, your answer is anonymous. If you get the wrong answer, it doesn't hurt at all. Nobody knows. We'll be able to see the results during the presentation, and it's a way to enjoy our time together, to participate in what otherwise would be a more of a one-way platform. Okay, so Marcus is going to help me run the poll question through Demio, and you're already starting to answer the question. I can see the results coming up. True or false? The DC current rating of a 2-terminal surface mount EMI suppression ferrite gives important information about its high frequency behavior. True or false? The current rating tells us. Let's see what the poll results are. Okay, we've got about 100 people that have answered so far, and it is split 50-50. I have to tell you something. As for the part of my job where I do teaching, I love poll questions. These are the most valuable kind of feedback I could ever receive. I should pay you for answering the questions because they indicate to me the knowledge base of people out in the world who are doing electrical engineering, and it tells me how I should change my course content. So we always survey at the end of classes. And when I do these online presentations, these poll questions give me really good insight as to what is common knowledge and what is not common knowledge. And so it's split about 50-50. We have about 120 answers right now, 125 answers, and it's about 50-50. That's very interesting. So I now have to give you the bad news. The bad news is the question is no. It does not give important information. The current rating for an EMI suppression ferrite only tells you about heating. It tells you about the temperature rise above ambient if you have that maximum current flowing through the part continuously. This is a little weird, especially for hardware design engineers who are super skilled, super smart in electronic design, but are not so interested in EMI geeky things like EMI suppression ferrites. When we buy an inductor for energy storage or to make a tuned circuit, to make a filter, we usually get 2 current ratings. We get a current rating that tells us about heating, and that's usually called an RMS, a current rating. And then we get a saturation current rating that tells us above a certain current level, we don't get the rated or printed value of inductance from the part. That's what we are, as design engineers, that's what we are accustomed to getting. Now, when we buy an EMI suppression ferrite, and I use those words, EMI suppression, like, why did I make the title of the presentation so long? Because I went to college? No, because I wanted to be very clear. I was talking about ferrites that are used to combat or to fight noise. There are lots of ferrites that are used for other purposes. There are lots of very interesting microwave devices that are used, and they don't incorporate loss into the part. They use the impact of ferrites a ferrite material to steer an RF signal in a particular direction, for example. So when I use the words EMI suppression in front of ferrite, I generally mean a ferrite that's used to reduce noise at frequencies generally above 1 megahertz, where we can get significant loss. We can add resistance into a circuit. If we have a resonant noise problem, we have a problem where a circuit has a favorite response at 1 or more specific frequencies, that loss can help us reduce the response of the system, and that will allow us to pass a regulatory test. It will help us solve a noise problem. So that's why I use those words EMI suppression ferrite in front of the EMI suppression in front of the word ferrite. So thanks again for participating in the poll. That's so kind of you, and it's fun to see the results. So today's presentation, what am I going to talk about? At the end, of course, we're going to have the fun demonstration, so I hope you'll hang around for only 30 minutes. We're going to talk about noise filtering with EMI suppression ferrites. We're going to talk about some very simple electrical models that describe an EMI suppression ferrite and would allow us to essentially construct a SPICE model if we wanted to do a simple model to represent what an EMI suppression ferrite does. And when I teach university classes, that's certainly one of the exercises, is to, given an impedance versus frequency plot, a curve, can you create an electrical model that would represent, or that a model that would generate that impedance versus frequency plot? So it forces us to understand, the first level physics of what's going on. At a very high level, we would say a macro model. We don't get inside and figure out exactly what's going on in the material, but we can observe some electrical characteristics. And of course, the whole point of the presentation is to see what happens when we have current, DC current flowing through a ferrite. Lots of times we have EMI suppression ferrites that we use to filter the DC wires that are leaving a circuit board, that are leaving a system enclosure, or the DC current that's going into an integrated circuit. And we want to understand what the impact is, because the current rating of the EMI suppression ferrite doesn't tell you what's going to happen at frequencies, at noise frequencies that might be trying to pass through that part. It doesn't tell you about that. It just tells you about heating. Of course, we'll have the live measurements. When I teach students who are still in university or who have just graduated, who don't have a lot of experience in noise at all, they have no practical experience, and it's a very abstract or kind of theoretical topic to them. They haven't worked with noise problems with their hands yet. I have a very simple way of describing filtering. In this case, we're going to talk about using a filter in series with the noise path. If the noise reaches the victim, that's a problem. We have 4 different electrical noise paths. It turns out that EMI suppression ferrites can be used to fix any one of those 4 noise paths. If you have a noise problem that's involving conducted coupling, that means there's 2 or more conductive connections between the source and victim. If we put EMI suppression ferrites in series with that noise current and we pick the right ferrite for the application frequency, we can reduce the conducted flow of noise current from source to victim. If we have inductive coupling, or maybe we could call it transformer coupling, we have a noise current flowing in the source circuit that acts like a primary, and that creates a magnetic flux. That magnetic flux, when it's shared with another circuit, another loop, it induces a voltage. But it's the current in the source circuit acting like a primary that causes the noise coupling. So if we can affect the current in the primary or the source circuit, we can reduce inductive coupling. If we have capacitive coupling and we have a time-changing voltage that pushes a displacement current into the victim circuit, that displacement current then becomes a conduction current in the victim circuit. So we can affect the amount of conduction current flowing in the victim circuit during capacitive coupling. So again, an EMI suppression ferrite could work. Finally, the 4th path, we have radiated coupling. Radiated coupling requires big distance between the source and victim, and it requires big objects. Those big objects are called antennas. If we have a radiated emissions problem, if we reduce the amount of current reaching the transmitting antenna at the source by using an EMI suppression ferrite in series with, let's say, the wires attached to the circuit board or the wires connected to the enclosure, if we have enough impedance there, we will reduce the amplitude of the current reaching the transmit antenna. Less current in the antenna, the less amplitude or a lower amplitude radiated field. If we have an immunity or susceptibility problem, we have an antenna converting an incoming radio wave or an incoming radiated power to a conducted power. That conducted power is created by a current flowing into the victim circuit. Again, an EMI suppression ferrite can help with that. So we can improve immunity and emissions problems. And in general, we want a big impedance. And our ideal 2-terminal EMI suppression ferrite, in this case here, we want it to have an infinite impedance. If it's an open circuit, none of that current from that external noise that's pushing a current in on an attached wire, That might be a conducted immunity problem. This might represent a radiated immunity or radiated susceptibility problem. If that Z is infinite, we have zero noise. So that's our goal. Bigger impedance is obviously better. That's what would fix a susceptibility or immunity problem. If we visualize that noise current coming from the inside of the system going to the outside, then we would call that an emissions problem. If we measure the current coming out on that wire, we might decide to call it a conducted emission. If we measure the field, a radiated field produced by that current flowing out on that wire, we might choose to call it a radiated emission. Human beings like to make everything really complicated. If you're married, you might have direct experience with that. Of course, I love my wife, but it makes things a little bit more complicated. Human beings like to make things complicated, and we talk about emissions and immunity, or susceptibility and emissions, as if they're two completely separate worlds in the world of physics, or in the galaxy of physics. And they're really not. If the current's flowing out, it's immunity. If it's flowing in, it's sorry, you know what I just said. If it's flowing out, it's emissions. If it's flowing in, it's an immunity problem. If we measure the current flowing out, oh, it's a conducted problem. But if we measure the field from the current flowing out, if we measure the field produced by that current, oh, it's a radiated problem. It's the same thing, right? There's energy in the current and in the field simultaneously. So again, we make things complicated. If we can reduce the current flowing out, we can reduce the radiated emission. If we can reduce the current flowing in, we can fix the radiated susceptibility problem. Okay, so blah, 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 blah. That is a lot of talking to say we want the impedance of the EMI suppression ferrite to be as big as possible at the noise frequencies we want to stop. Okay, so technology, there's lots of buzzwords. If you're relatively new to the world of EMI, you're faced with a lot of different words. So EMI suppression ferrite, you'll hear people say chip bead, ferrite bead, SMT ferrite. They all pretty much mean the same. If they are used for the attenuation of noise, for the reduction of noise, the primary mechanism is going to be loss. That's what we really like, is that loss. That's like adding a shock absorber or a damper to an automobile suspension. Energy gets exchanged between the car body and the spring when there's a velocity input into the wheel, when the wheel hits a bump or a hole in the ground, right? And if we don't have a damper or a shock absorber, the car body goes whing, 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 whing. So we use that loss in the damper or shock absorber to make the ride nice and smooth, to stop the big excursions, the big maxima and minima that we would get in the car body. That's analogous to the big voltage or big current peaks we would get during a resonant condition that in an electrical circuit that we would notice as a noise problem. When we say EMI suppression ferrite, generally speaking, we are not using them for energy storage. If we build a switch mode power supply, a buck or boost with a 2-terminal energy storage inductor, we don't want to lose any of that energy in the inductor as heat. So we want a low loss inductor, right? But EMI suppression ferrites, please give me the loss, give me lots of resistance. It's a 2-terminal device with a magnetic core. The current ratings range from milliamperes to amperes. There are many, many different available different parts that you can buy. The sizes range from, I bet there's parts that are smaller than 0201 now. I didn't check before I wrote this presentation, but they range from very small to very big, and they work over a very wide frequency range. Of course, the parts are not open circuits or short circuits below 1 megahertz. I mean here, greater than 1 megahertz, I mean where we start to notice significant loss in the parts. We'll talk a little bit more about how these parts work over that entire frequency range. Of course, they conduct current below 1 megahertz. If they didn't, this DC bias demonstration would be kind of dumb or not possible. Here's a simple model for a 2-terminal ferrite. I'm going to show you 2 different electrical models. So the important parameters here are in the middle. The R, that's the core and wire loss, mostly the core loss, the conversion of energy to heat in the core. Now, That's generally not something for a surface mount ferrite. You're not going to put your finger on the ferrite and feel it's getting hot from noise current. That would be unusual. We have some inductance, of course, and then we have some capacitance across the terminals. This model is correct or consistent with the device physics, with the R in series with the L. That is, if current, if we couple magnetic flux to the core because a current is flowing through the conductor within the part, if we create magnetic flux, we also create loss. You have to have both. If the current doesn't, if the current kind of jumps around the terminals of the part, if it flows through the C, then it can avoid the resistive loss of the conductor and the core loss. So that's what happens at high frequencies. So when we think about what happens with this model over frequency, so if I put frequency on the x-axis and z magnitude on the y-axis, at very low frequencies, it's almost a complete short circuit because the core losses and the wire losses are negligible, and the inductance, 2 pi FL, the inductive reactance, is essentially 0. So at low frequencies, it's almost 0. At high frequencies, the capacitance forms a short circuit, it's almost 0. And somewhere in the middle, the impedance has to peak, right? So that's what we'd expect. Very low at low frequencies, low at high frequencies, and somewhere in the middle, it peaks. And at the resonant frequency, we get big loss, and that's what we at this where the impedance is maximum. That's where we get the most amount of loss. Okay. Then we have this other model where we have the R in parallel with the L in parallel with the C. This is not consistent with the device physics, but it makes it easy to measure. So if we measure this on an impedance bridge and we measure 2-terminal impedance at resonance, that is, resonance means where the impedance is maximum on impedance versus frequency. If we measure this number of ohms right here at this frequency, that is going to be the value of loss of the part. And EMI engineers like that big resistance. That's the shock absorber that will chew up. It'll chew up the noise current, and it'll convert some of that conductive power to heat. Okay, those are the models. Now, where did that resistance come from? How do we think about that? Well, it's these EMI suppression ferrites. They're kind of strange devices. The resistance is a function of frequency, and their inductance is a function of frequency. And that's a very easy circuit to understand. Okay, and the way we get to understanding the loss is that we model the magnetic conductivity of the core as being a complex number. So instead of just saying the inductance is due to the permeability of the core and have a single real number, we show it as a complex number. And then we do a little bit of math and plug in that complex number where the permeability normally is, and we come out with a complex number where the real part depends on the imaginary part. You see that mu double prime here? That's the imaginary part of the permeability. And the bigger the mu double prime, the greater the loss of the part. Now, how do you get big mu double prime? Well, you have to have a trade secret about the recipe. How do you bake the ferrite? What ingredients do you put in your cooking pot to make that clay, to make that material that we then put into the hot oven to make the EMI suppression ferrite, or that when we make layers of this material in a wet process, the mu double prime depends on what we put in the magnetic core, what ingredients, what elements we put in there. Okay, so that's where the loss comes from. We make the permeability be a complex number. All right, this is a typical impedance curve for a 2-terminal ferrite. Okay, so this curve shows this graph shows 3 curves. We have the red curve, which is the magnitude of Z, right? Then we have the R, which is the resistance, and then we have the X, this bottom curve here, which is the inductive reactance. If you look at this frequency, it's around, it's right around here, around 50 megahertz. If you look at around 50 megahertz and you think about what does this 2-terminal device look like above 50 megahertz, you would say, well, let's see, the red curve, the Z, and the blue curve, the R, they are getting very, very, very close together. Here's the Z curve and here's the R curve. When the Z is essentially the same as the R curve, we call that a resistor. So above 50 megahertz, we might call the EMI suppression ferrite a high frequency resistor. And that's what people do. They call them high frequency resistors. And that's of course very true. But what if we take a look at another frequency on the plot? What if we look at down here, down at the bottom of to the left part of the x-axis? What if we look at 10 megahertz? Around 10 megahertz, you see the magnitude of the impedance is essentially the same thing as X sub L. From 10 megahertz and down, what do we have? We have a pure inductance. Very high impedance, two-terminal EMI suppression ferrites, very high impedance parts, like 2,000 ohm, parts that reach 2,000 ohms at maximum. At low frequencies, they can have as much as 1 microhenry of inductance. Some circuits don't like 1 microhenry in series with them. So of course, we would like to use a SPICE model that tells us how the circuit will perform to be able to simulate how our intended circuit will work when we add that EMI suppression ferrite in. So be a little careful of that at very low frequencies. These higher impedance parts can have a significant amount of inductance. But we like these parts because they have that big, wide region where we have lots of resistance. Now, if you get just this one plot from the vendor, this is the performance of the part when it's turned off with the net DC current equals 0. Okay, I like to know how my parts work when we do actually put current through them. And here's what happens. Here's a 500 milliamp device rated at a maximum value of 600 ohms. Here's what happens when we increase the current through the part. The peak impedance is a function of bias. Each curve represents an increase in DC current flowing through the part. You see that this is a 500 milliamp device, but we wouldn't know what this characteristic looked like. We wouldn't know how these curves move from left to right across the frequency axis. So the red curve, that's the magnitude of the impedance that I showed you on the previous slide. As we increase current, we see that the peak impedance moves up the frequency axis. And if we look at frequencies only below the zero bias resonant frequency, we will see what appears to be a drop in impedance as we increase current. This could be a very sneaky behavior if your system that you're using an EMI suppression ferrite in, if you're using one to stop noise current, and you increase the DC current draw, so you add maybe LEDs to your circuit and you cause more current to be drawn, you might get different noise filtering performance, because that's how this is the nature of these parts when they're exposed to a net current. Okay, so you see the peak impedance drops a little bit with increasing frequency, but more importantly, you see the frequency at which the impedance peaks. You see the peaks are moving up the x-axis. Okay. The Q, the width of the curve, the frequency range over which we get some significant impedance is reduced. So more current, a narrower frequency range where this part can stop noise current. Okay, if you pick the wrong part, if you try to fix a 1 gigahertz problem with this particular EMI suppression ferrite, bias doesn't matter. You should have picked a better part. But the point is, wow, below the frequency that's indicated by the red curve, that's the zero bias curve, when you look at essentially the operating characteristic, you get a much different impedance level as DC current flows through the part. So this is not, you can't figure these curves out from just that current rating of the part. That current rating only tells you about heating. You either need these plots from the vendor, like from Würth, or Würth gives you a SPICE model that has a current input terminal, and you can tell the part, okay, pretend that you have 100 milliamps of current flowing through you at DC, show me your impedance. And you can derive these curves yourself using the Würth SPICE models. Okay, so the DC current rating does not tell you about its high frequency behavior. It only describes the heating. Okay, so what did we see and learn? We're just about to get to the demonstration and complete the presentation. The current rating of an EMI suppression ferrite only describes the effect of temperature rise. It doesn't describe the impact of bias on a device's impedance versus frequency characteristic. DC bias can have a very strong effect on the impedance versus frequency curve. And as I mentioned, Würth supplies SPICE models that you can derive your own impedance versus frequency plots very easily. Okay, so now what I would like to do is I'd like to show you the demonstration that I'm going to do, and that's going to involve a handmade two-port test fixture with a DC bias input. So I'm going to put DC, right in the middle of this bias fixture, I've got an EMI suppression ferrite bead. And I'm going to use a desktop little vector network analyzer that I can control with the USB port, and I've got a little programmable power supply. So let me show that to you on the bench here. In the next 5 minutes, I'm going to take out of the question and answer period. I got my vector network analyzer here. There's a USB cable exiting it right up there. The vector network analyzer is connected through the semi-rigid coax to my test fixture, and I showed this test fixture to you before. Inside of this is a circuit that I designed to provide DC current in and an RF path in and out. It's not very fancy. And then you can see the two red clip leads here. That's going to provide a current in and out. So we're actually going to be providing a current into and out of the ferrite bead simultaneously while we run a signal through it. Okay, and then the computer-controlled USB power supply will allow me to send in a fixed current. You see a big chunk of stuff here. I put an external series resistor here because I don't trust the current limiting of this power supply. I want to make sure I don't burn up my circuit board here, and I can easily control current from this power supply. Okay, so what we're going to do is we're going to use a vector network analyzer to send a signal through here. From that, we're going to derive the two-terminal impedance, and we're going to watch the impedance loss and reactance of this part change with a change in bias. Okay, so let's take a look at that right now. This is the plot from the vector network analyzer. The horizontal axis is frequency. It's running from 1 to 500 megahertz. It's live right now. And the vertical axis is 275 ohms per division. So you see right here, the peak, you can't see it because I don't have the slide on. There you go. Okay, this is the results of the vector network analyzer right now. Okay, so the x-axis is 1 megahertz to 501 megahertz. The vertical axis is in 275 ohms per division. There I am. And you can see the black curve is magnitude of impedance, the blue is the resistance, and the red is the inductive reactance. The resonance here of impedance and the reactance going through zero doesn't quite line up. For those of you who are good with vector network analyzers, that's because I don't have a perfect calibration. Okay, now what I want to show you is that this is a live measurement, and I'm going to go stick my finger right in here. It's safe to touch. I'm going to go affect impedance versus frequency by putting my finger in there, and you can see as I get a little capacitance in there, I shift the measurement result down a little bit as I add capacitance. So I'm just proving to you that it's live. Okay, and then I'm going to go turn on the power supply that you can see. I'm going to turn it to on. Now, don't worry about the voltage level. It's the current rating, that's the current, the present value of current that matters. So as I increase voltage, I'm going to push more current and watch what happens to these curves. Do you see it? The curves going down, 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 and then going up to the right? Isn't that cool? That's only 60 milliamperes. That's only 70 milliamperes. That's 100 milliamperes. And you can see that the magnitude of the impedance, the loss, and the reactance are all moving together. What's this wiggle, wiggle, wiggle over here on the right-hand side? That's actually a noise problem, right? That's a noise problem between my external USB hub and the USB connection to the vector network analyzer. I could get rid of that, but give me a break. I don't want to have to fix a noise problem when I'm trying to demonstrate one. All right, so you can see that as I reduce current, the impedance plots return back to where they were. So you can see right now live the effect of current on bias of a two-terminal ferrite. You know, it's one thing to look at printed pictures on a data sheet. It's another thing to do a SPICE model, but I think it's fun to see that measurement live. I hope that you enjoyed that. Okay, so this is the equipment that I use today, the little two-terminal test fixture. I showed you that picture before. So right in the middle of the test fixture, it's really hard to point out with my fingertip, but there's a ferrite bead in series with here. There's all sorts of inductors and capacitors in the DC bias path. And I can demonstrate to you how good this the the bias network is. I'm going to disconnect the power supply. I'm going to disconnect the power supply from the fixture, and I'll just show you one more thing here. I'm going to take the, I'm just going to take one of these alligator clips while I show you the measurement over here on the left side. There, that's not the right, that is the right side. Let's see if you can see that right now. Last thing. Yep. And I'm going to put the alligator clip directly across the bias terminals. So I'm going to put a short circuit across the bias. And what you see is essentially no change in the plot at all. There's a tiny little change at the low end, but basically I'm showing that the DC port is perfectly decoupled from the high frequency measurement as I put a dead short right there across the bias terminals. So that tells me that my bias port is working very well. It's only conducting DC current and it doesn't affect the measurement. Okay, that's what I have for today. I'll also show you measurement equipment that we use at work. There's information about our courses. And I want to thank you very much for attending the presentation on EMI suppression ferrites. I'm going to go and take a look and see if we can handle a few of the questions that have come in right now. And let's see what we've got here. If I can answer a couple of them. Got a lot of comments. And
yeah,
let's see. So then it's okay if I go read off the chat questions here?
Yeah, of course. But also maybe I have also a question for you. How can you still be so motivated after all those years? I really enjoyed your presentation. So thanks a lot for your presentation today.
You're welcome, Marcus. So at this point in my career, I ask myself every day, why am I doing this? and my answer is, I want to pay it forward. I want to continue to teach and give knowledge to other people who are maybe a little bit earlier in their career than me. So that's, and if I'm not providing enthusiasm, if I'm not providing energy, I can't imagine why anybody sitting in a class with me, listening to the class, watching the class, should have any enthusiasm at all. I think that's my job as an instructor. That's my short answer. So let's see what the questions say.
Yeah, of course. Thank you very much.
Let's see.
So then, yeah, sorry. You can just go ahead. That's fine.
Okay, I obviously had my coffee this morning. Is the low frequency inductance of a ferrite bead available in the data sheet? Can it be found somehow? So the answer is yes. If you took a look at one of the, let's see, at this plot right here, for example, the zero bias plot. If you look down in the bottom of the screen, you will see where the impedance is rather linear with frequency. Well, we're on a log plot, so we're on log frequency and linear vertical axis. Up to some frequency where z is equal to x sub L, it should be very easy to just say the magnitude of the z is almost entirely equal to 2 pi FL, and you could extract out L very easily. I think it would be unusual to see a single value of inductance printed on the data sheet. Yeah, that would be confusing because we're not going to use an EMI suppression ferrite as a low frequency storage inductor. So presenting inductance information would have to have a lot of, asterisks and, it depends. Short answer is yes. Just look at the low frequency part of the characteristic where the impedance and inductive reactance curves are essentially coinciding. Would you recommend to use ferrites in parallel to increase the impedance because of the split of DC current per ferrite? I suppose you could do that. I have never done that. The difficulty would be the resistances of the two parts might not be equal. So this is a very old story of power electronics, of trying to put devices in parallel for increased power handling capacity. And you would have to somehow ensure that the same amount of current was flowing through each part. So you're going to get if you have two identical parts, the impedance is going to divide by 2. The bias effect is not linear. So I think you would gain some benefit, but the real question is, are the resistances of the parts, the DC resistances, are they close enough to ensure fairly good sharing of that current? I think you might end up overheating one part on a very unlucky day. if you had a lot of current. At a low current, if the maximum current that you're going to put through that parallel combination is below the maximum current rating of one of the two parts, then you would be safe. But the question is, how much will you actually achieve? You know, how evenly will the current be shared? All right, so I'm going down the list here. Excellent. Why most of the ferrite bead suppliers are not providing the impedance versus current graphs? Okay, well, I like working with Würth, so you probably won't like my answer if I say they're not as smart as Würth. I don't know, that is the answer. Okay, do we need to have a special simulation model for the bead to see the DC bias effect? Absolutely, and that's what Würth provides, a SPICE model that has a DC current input so that you can create and derive those curves yourself. Yes, you do, right? Does it not work the same if we just apply a DC source to the simulation and use a model with 2 pins? No, that won't work. The model has to have information about the impact of bias built into it. All right, blah, 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 blah. Does including the ferrite bead for data signals affect the performance? Okay, well, that's a basic question about, does the ferrite bead introduce significant impedance at signal frequencies? So we'd have to think about what is the bandwidth of the signals that we want to push through the EMI suppression ferrite. I would say, generally speaking, you know, we would use an EMI suppression ferrite when it's in series with a signal. We would say we want the ferrite to be a low pass filter, low frequency signals and current flow through unaffected. When we use EMI suppression ferrites in series with a signal, we need separation on the frequency axis between what we call signal energy and what we call noise. All right, and we have maybe a couple more minutes.
Yeah,
if you
so I also just shared the handout of the slides, so you're now able to download them as well. But yeah, then we will just need, or we will use the last minutes to answering the other questions. And if you have still any questions left, or we don't have the time today, we will answer them later on. Okay.
Excellent. All right. So I think there's maybe one more here. And for those of you who are just chatting in, thanks for the presentation. It was great. Or those sort of just nice statements. Thank you very much. That definitely keeps me going. That keeps my energy up and makes me wanting to do this again. So thanks for saying the nice things there. If you put two ferrites in series, is the total impedance twice as high? Yeah, it's 2 times what you would have had before. Of course, there's a very, very small thing we should talk about, that we have to assume that the physical path through the 2 series elements is electrically short. That is, each ferrite bead sees exactly the same noise current. Because if the beads are separated by a significant amount of distance, we will get an effect that doesn't quite look like 2 parts in series. We're thinking that the 2 ferrites act as one in series, and that means the total path length has to be very short compared to a wavelength of the noise current flowing through it. There's a question here that's a little too general for me to be able to answer in 1 or 2 sentences. Your recommendation for terminating ferrite beads to suppress resonant points. There are application notes and tricks about putting a resistor in parallel with a ferrite bead to provide some damping. Resonance points, I think, if resonant points means in the actual application circuit. So this is a pretty tough question. If we could talk about that offline, that takes a little too long to make sure we know what we want to say. Okay, one last question. I'll take this last one, Marcus, and we'll call it a day here. Can you recommend the use of the ferrite beads up to 20% of rated current and still be close to the datasheet graph? Okay, can you recommend that essentially you use a ferrite at only 20% of its rated current so that you can get the datasheet graph? I think you mean the zero bias plot. My short answer for that is be really careful. Each ferrite bead has a very different personality, and the plots that I showed you in the graph are in my presentation are very specific to one part. Some parts have very little impedance change with bias currents, and some parts have a big one. So you can't generalize to 20%. You have to pick a specific part and then examine what happens at 20% of maximum current. Okay, thank you all for sending in so many questions. And Marcus and Würth, thank you so much for inviting me to present during Würth Digital Days.
Yeah, Lee, thank you very, very much from our side. It was a pleasure to have you here. And yeah, we also see the reactions from the attendees. So I think it also was a pleasure for them to hear to you. And yeah, so then I would say thank you very much. Stay tuned and yeah, have a nice day.
Take care. Bye-bye.